High-performance liquid chromatography, or HPLC as it is commonly known, is an important analytical technique used to gain both quantitative and qualitative data for samples produced in a variety of industries, such as pharmaceuticals, food products, and industrial chemicals. The purpose of this guide is to consider this question: what is a HPLC instrument? We will focus on analytical applications. The implementation of HPLC requires the use of precision instruments. There are two main reasons for this. The first is that sophisticated instrumentation is needed to create suitable method conditions, and the second is that reproducible control of these conditions is critical. A HPLC system can at first glance appear daunting to the new operator. A full understanding of the components common to all HPLCs can transform bewilderment regarding a complicated arrangement of tubing and electronics into an appreciation of a logical and well-designed piece of analytical equipment. At the heart of all HPLC systems is the column. This is where the separation of the components of interest in your sample actually takes place. It is the interaction of the stationary phase contained in the column, the mobile phase, and the sample components, which forms the basis of this analytical technique. The stationary phase in your column is typically, but not always, in the form of very small spherical particles. The diameter of these particles is in the order of a few microns, that's 1/1000th of a millimeter. In analytical HPLC, the particle size diameter ranges from approximately 1.5 to 10 microns. To achieve a separation, we need to create a flow of mobile phase through the column. To enable this, tubing is connected to the ends of the column. The very small size of the particles means that a flow of liquid needs to be pushed through under high pressure to get a reasonable flow rate. As a consequence, the tubing needs to be connected in such a way so as to withstand the high pressure. This is achieved by the use of compression fittings. These fittings screw securely into the ends of the column to create a leak-free connection. So far, we have a HPLC column connected by tubing and compression fittings to the mobile phase reservoir. We will add a vessel to collect the waste at the other end of the column. To keep the mobile phase moving through the column at a steady flow rate under pressure, we need to introduce a pump in the flow path. This instrument is designed to draw the mobile phase from its reservoir and deliver it to the column at the required flow rate. Now we have a flow of mobile phase through our stationary phase, but we need a way to introduce the sample for analysis. For this, an injector is required. This instrument is designed to inject a small aliquot of sample, typically in the order of a few microliters, into the flow path of the mobile phase prior to the column. It has to do this without altering or stopping the flow of the mobile phase, and thus maintaining the system pressure. In most modern systems, this process is automated, and samples are placed in vials which can be injected by the autosampler in the order and amounts programmed by the operator. When the sample has been injected and passes through the column, the separated components need to be detected in some way so as to convert the results of the analysis into useful data. The detector is designed to be able to recognize some characteristic of the sample component. The most common detector is probably an ultraviolet or UV detector. This works by passing a beam of UV light through the flow path of the mobile phase, measuring the absorbance. For those components which absorb UV light, the response obtained will be proportional to the amount of the component present. Not all components absorb UV light, and those that do have different responses, so these factors need to be considered when choosing a suitable detector. There are a range of different detectors available which may be used for HPLC. These include MS, which passes the flow coming out of the column into a mass spectrometer, thus obtaining information on the amount and molecular weight of the compound. Other detectors which you may have encountered include evaporative light scattering, charged aerosol, fluorescence, and conductivity detection. Some kind of processor is required to convert the responses from the detector into usable data. Purpose-designed software applications called chromatography data systems are available. Common examples are mPower, Clarity, Chromalion, and EasyChrome. In gradient analysis, the composition of the mobile phase is changed during the course of the analysis. To enable this, we need another mobile phase reservoir and some way of mixing the two. The mixing may be performed before the pump as shown here, in which case it is not yet under pressure and is called low pressure mixing. Or the mixing may be performed after the mobile phase flows through the pump, in which case it is under pressure and two pumps will be required. Systems which use high pressure mixing are often referred to as binary systems, since two pumps are needed. In practice, low pressure mixing with a proportioning valve before a single pump is most commonly used. Another instrument which is typically included in a HPLC system is a vacuum degasser, since all air needs to be removed from the mobile phase for optimum performance. Temperature is an important method parameter which needs to be controlled in HPLC analysis. For this reason, the column is often housed in a compartment which can be temperature controlled. Many HPLC systems have the capability to mix 4 mobile phases. These are known as quaternary systems. So what happens during an analysis? The mobile phase is flowing through the system from the mobile phase reservoir to waste. We will inject a mixture of 3 components, shown here using 3 colours: pink, green and blue. At the head of the column, when the sample first encounters the stationary phase, we have a mixture of all 3 components. The equilibrium between each component, the stationary phase and the mobile phase is different for the 3 colours in the mixture. In our mixture, the pink component spends more time in the mobile phase relative to the green and the blue, and travels through the column quickest. The blue component, however, spends more time on the stationary phase relative to the other 2, and travels through the column slowest. As the mixture passes through the column, they become more and more separated. The pink components leave the column first, and on passing through the detector, a peak is observed on the processor. Then the green component passes through the detector, resulting in another peak, and finally the blue component passes through and has a corresponding peak. This plot of the separated peaks is referred to as a chromatogram. Overall, the blue component spends more time in the flow path and has more time to spread out. This results in a broader peak relative to a component which has passed through in a quicker time, such as the pink in this example. It depends on the actual method parameters being used, whether this band broadening effect is as noticeable as it is in this example, where you can see that the peaks are progressively broader as time passes. Now that we have looked at the individual components of a typical HPLC instrument, you should be able to look at the system that you use in your laboratory and understand how it works. This video is provided as an example of the training resources available from Moore Training Services. Visit the website for more information on our training solutions for pharmaceutical analysis. Please feel free to use this video in your HPLC training programs.
طبعا يا شباب، بعد ما شفنا الفيديو ده، هو طبعا الفكره هنا في نقطه بس عايز اكد عليها. هو طبعا في نقطتين هي اتكلمت فيهم بتفاصيل شويه، اللي هي فكره الميكسرز او الموبايل فيز ميكسرز والديتكتورز. طبعا انواع الديتكتورز اللي هي ذكرتهم احنا كده هنتكلم عليهم. هي الفكره كلها ان احنا بيبقى عندنا انواع مختلفه من الديتكتورز، وكل نوع بيشتغل وبيديتكت الكومبوننت بيزد على بروبرتي معينه. بس زي اليو في مثلا كده ديتكتور، زي ما هنشوف بيديتكت مثلا اليو في ابزوربنس وهكذا. الحاجه الثانيه اللي هي اتكلمت عليها ودي نقطه مهمه قوي، الموبايل فيز ميكسرز. الموبايل فيز ميكسرز دي معناها ايه؟ معناها ان مش شرط يكون عندي ريسيرفوار واحد. لو عندي ريسيرفوار واحد او بوتل واحده، المفروض ان هيكون فيها موبايل فيز واحد، زي مثلا الميثانول مثلا. نفترض ان انا مش عايز استخدم ميثانول بس، انا عايز استخدم ميثانول ومعاه مثلا اسيتونايتريل. يبقى في الحاله دي لازم يكون عندي ريسيرفوار تاني فيه اسيتونايتريل، ويبقى عندي حاجه بتعمل لي ميكسنج للاثنين مع بعض ببروبورشنز معينه او بنسب معينه انا بحددها له. انا بحددها للسوفت وير. يعني انا بقول للسوفت وير مثلا انا عايز السولفنت سيستم بتاعي يكون 60 اسيتونايتريل 40 مثلا ميه، او 60 اسيتونايتريل 40 ميثانول. فبالتالي هو بياخد 60 من هنا و40 من هنا ويعمل لي الميكسنج ويدخل لي الميكتشر ده على البامب بعد كده ويرفعها على بعد كده على الكولر. فهمنا؟ هي دي فكره الميكسرز. عشان كده هي بتقول لكم ساعات في الفيديو بتقول لكم ان احنا عندنا في بعض الاحيان عندنا حاجه اسمها كواترنري سيستم. كواترنري يعني ممكن يبقى عندي 4 سولفنت ريسيرفوارز وفي ميكسرز بتشتغل انها تعمل ميكسنج لبروبورشنز من الاربعه. تاخد من هنا ومن هنا ومن هنا من الاربعه دول بنسب، وتجمعهم مع بعض وتبعتهم على الايه، على الكولوم. فهمنا؟ هي دي فكره بس الميكسرز، ودي بتفيدني قوي على فكره يا شباب في الجريدينت illusion. ان انت في الجريدينت illusion لما بتيجي تعدل زي ما هنتكلم بعد كده، فاكرين الايزوكراتيك والجريدينت ده من الاسئله المهمه قوي اللي هسال فيها الفرق بين الاثنين. الجريدينت دايما بتبقى فيه تعديل في البروبورشنز بتاعت الايه، بتاعت الموبايل فيس، وبالتالي يبقى التعديل ده بيتم من خلال الميكسر، ان انت بتدي اوردر للميكسر ده عدل لي النسبه، غير لي النسبه بدل ما هي 60 40 خليها 50 50، فيقوم هو معدل النسبه اللي بياخدها من السولفنتس المختلفه او من الريسيرفوارز الايه، المختلفه. تعالوا نشوف الفيديو التاني بقى. الفيديو التاني ده بيوريك الدنيا على الطبيعه بقى، يعني حد واقف شغال على جهاز HPLC.
HPLC stands for High Performance Liquid Chromatography, but could equally well stand for High Pressure Liquid Chromatography. It is used for separating mixtures, either to analyze the mixture or to separate a required product from others in a reaction mixture. It can also be used to find the relative amounts of different components in a mixture. HPLC works on the same principle as paper chromatography, here shown speeded up. A liquid, called the mobile phase, moves past a solid, the stationary phase. In paper chromatography, this stationary phase consists of water molecules bound to the cellulose in the paper. The mobile phase carries different components of a mixture, called the sample, along with it at different rates. How fast each one moves depends on its relative affinity for the mobile and the stationary phases. For example, if the mobile phase is more polar than the stationary phase, the more polar components of a mixture will tend to move more quickly than the less polar ones. In HPLC, the stationary phase is a solid packed into a column, like one of these. This particular column contains silica particles to which C8 hydrocarbons are attached, making the stationary phase non-polar. In paper chromatography, the solvent moves along the paper by capillary action. In HPLC, the liquid is forced through the column by high-pressure pumps. The whole apparatus looks like this. These bottles contain solvents. Two solvents can be mixed in any proportions to give a mixture, the liquid phase, of suitable polarity for the separation that is being done. In this case, one solvent is water, very polar, and the other ethane nitrile, less polar. The operator can decide on a mixture with the correct polarity for the separation she is doing. These are the pumps. They produce a pressure of 15,000 kilopascals, 150 times that of the atmosphere, hence the name high-pressure liquid chromatography. If a single sample is to be run, it is injected into the solvent stream here, in the injection port, via a hypodermic syringe. Alternatively, several samples can be run in succession by loading them into this auto-sampler, which will run them in order without any human intervention. The pumps force the mixed solvents through the column. The solvent emerging from the column and carrying the separated components of the mixture passes into the detector. Here, a beam of ultraviolet light shines through it. This light is set at a wavelength that is absorbed by all the components to be separated. When the detector reading drops, a component that is absorbing UV light is coming out of the column and passing through the detector. Many alternative types of detector are possible. This one measures refractive index. The time that each component takes to come off the column is called its retention time and can be used to help identify it. Here, the HPLC instrument is being used to separate a mixture of two steroids used in a pharmaceutical preparation. The column chosen is packed with a non-polar solid. The tails of the molecules represent hydrocarbon chains C8H17. Having chosen the solvents, detector wavelength and flow rate, a single sample is run by injecting about 20 microliters into the injection port. The more polar component comes off the column first, followed by the less polar. The peak at retention time, 1.5 minutes, represents other ingredients used in formulating the product. This is the pharmaceutical product, and behind it, its chromatogram.
تمام يا شباب، يبقى ده بالنسبه للايه اللي برضو الطريقه. طبعا لو لاحظتوا هنا اللي بصينا كده على اتش بي ال سي سيستم ده، هتحس ان هو كان اكبر شويه في السايز من اللي احنا شفناه في السلايدز الاولانيه، لان ده كان اقدم شويه. فزي ما قلت لكم دايما ان في الصناعه دايما بيدوروا على اللو ديسك سبيس، اللي هو ان الاتش بي ال سي يبتدي يصغر حجمه على قد ما بنقدر، ويؤدي طبعه يبقى مور افيشنت كمان عن الاول، وفي نفس الوقت ما ياخدش مساحه كبيره. عشان كده ده جهاز قديم شويه اللي هي شغاله عليه، عشان كده باين ان هو واخد مكان اكبر بكتير من الاولاني. انما على الاقل احنا كده شفنا السيستم، فهمنا الفكره العامه، وعرفنا ايه الكومبوننتس وايه فايده كل كومبوننت منهم بشكل عام مش بشكل تفصيلي، ولكن هو ده اللي يهمني في المرحله دي. خلاص، اخر فيديو هنتكلم عليه دلوقتي اللي هو فيديو بيوريك البريباراتيف اتش بي ال سي. الفيديو ده فيه تفاصيل كتيره قوي، فيه تفاصيل كتيره جدا، ولكن احنا هنتكلم بس مينلي على بعض الحاجات اللي هي او عايزك تركز بس على شكل الفراكشن كولكتور عامل ازاي، بيجمع الفراكشنز ازاي. بس مجرد ان انت تبقى شفته، مش عايز تفاصيل ولا عايزك تقعد تذاكر فيه ولا اي حاجه، مجرد بس انت تبقى شفت شكل الفراكشن كولكتور ده وتخيلته عامل ازاي. تعالوا نشوف سوا.
The Waters Auto Purification System for Preparative Scale Chromatography. Preparative scale chromatography plays a critical role in applications where compounds must be synthesized, identified, isolated, purified, characterized, screened, and tested. Purification is used to isolate compounds for drug discovery experiments, to isolate unknown impurities or metabolites, and to purify standards, natural products, and biomolecules. Waters purification systems offer scalable prep configurations, whether you want the specificity of a mass-directed system or the inclusiveness of a UV system. The Waters Auto Purification System consists of a 2545 binary gradient module, an injector collector, the 2767 sample manager, a system fluidics organizer for automated column switching, and a 2998 photodiode array detector. Optional detection techniques can also be used, such as single or tandem quadrupole mass detectors, a 2489 UV vis detector, or a 2424 evaporative light scattering detector. For mass-directed systems, a 515 makeup pump is included. The system performs analytical and preparative chromatography via separate flow paths. Unique solvent delivery technology enables the pump to deliver analytical flow rates to the analytical injector, and then much greater preparative flow rates to the preparative injector on the same autosampler. An analytical evaluation of a crude sample is performed to determine if purification is necessary. A small amount of the sample is injected through the analytical valve of the autosampler. The sample is separated on the analytical column and sent to the detectors. When purifying the compound, a larger amount of the sample is injected through the preparative valve of the autosampler. The sample travels through the prep column and is split between the detectors and the fraction collector. Fraction collection software monitors the data and controls collection. In a system equipped only with UV detection, any peaks that achieve the required threshold are collected. When collection is triggered by the mass spectrometer, only the specific mass or masses of interest are collected. This increases the overall efficiency of the purification system. The MS detector is a destructive detector, so a splitter is required to pass 99.9% of the preparative flow to the collector. The remainder of the sample is sent to the detectors, carried by the makeup flow from the 515. When flowing analytically, the alternative flow path does not pass through the splitter, but instead flows directly to the detectors. Before fractions are removed from the collector, a small portion of the fraction can be tested analytically. This will provide the operator with an indication of its purity before further steps are taken. Automatically generated reports from each stage can be emailed or displayed depending on preferences. All the steps in the purification process are automated through Water's Fraction Links Application Manager. The OpenLinks Open Access Application Manager can make the process accessible to any chemist. The auto purification system from Waters is designed to make purification highly accessible and available to satisfy all your laboratory's needs.